Well, so it's a great pleasure to be visiting the Newton Institute this term and to have so many interesting people to talk to. What I want to tell you about today is some work that I have been doing, which I started with Peter Symonds, but I've been continuing on my own since we actually wrote the paper. And it's about what happens when you tensor modules for a finite group. So my intention is that the back blackboard I'm going to try and use for things that I want to stay, so that I don't have to use it so much. So the front blackboard is where I'm going to start. So G is going to be a finite group. And K is going to be a field of characteristic P. And I may as well assume that it's going to be algebraically closed. It's not strictly necessary, but there'll be various things I say that I should have to modify if I didn't assume it was algebraically closed, but you can still say them, but differently. So the question is, if M and N are KG modules, how does M tensor N decompose? That's so the tensor operation in representation theory is just one of those things that causes a lot of problems, and it's quite difficult to get at. And of course, this question is much too broad. I'm not really certainly not going to answer it. So, a sort of sub-question is, how does a tensor power decompose? So we're going to, later on in the talk, not quite yet, we're going to put all these in the context of a representation ring, where we have a basis of the indecomposables, and it sort of encodes how tensor products work. But for the moment, let's not do that. Let's, for the moment, just have an example. So, of course, this question is interesting even in characteristic 0, but I'm going to mostly be talking about characteristic P. Let's take cyclic group of order 5 in characteristic 5. So we know what the indecomposable representations of that look like. Oh, by the way, in general, if you're looking at modular representations of a group, you can't classify the indecomposables. Usually you can't classify the indecomposables. There are unclassifiably many of them. Most groups have what's called wild representation type, which means you shouldn't really start trying to classify them. So my module, so what are modules for this? They're just, the indecomposable modules are just Jordan blocks of length between 1 and 5 with eigenvalue 1 for the group element, for your generator. So I'm going to choose a Jordan block of length 3 as my example, like that. Okay, and then we ask how this, how the tensor powers of this behave. So, so what is n tensor n, for example? Well, that decomposes as trivial plus n plus a projective. The projective indecomposable is just the 5-dimensional Jordan block. So projectives are just sums of 5-dimensional Jordan blocks. So, and if you tensor a projective with anything, you get another projective. So we sort of regard the projectives as the things we understand very well, and we get rid of them and look at all the non-projective stuff. Okay, So if I start taking tensor powers of n, the projective stuff is going to accumulate pretty quickly. And most of it's going to be projective after a while. So if you throw away all that junk, what's left? So this is really saying, if I mod out the projectives, that m squared is 1 plus m, if you like. Well, I can solve that equation. What is m? Is 1 plus root 5 over 2, right? Or it could be 1 minus root 5 over 2, but I really don't want it to be 1 minus root 5 over 2. Because what's this really saying? What this is saying is that if I take large tensor powers, the dimension of the non-projective part is roughly that power of this number. So let's define the core of a module is the non-projective part. So in other words, I decompose a module as a sum of something with no projective summands and a projective module. And that first summand is my core. And so if I take, in this example, the dimension of the core of m tensor n is roughly 1 plus root 5 over 2 to the power of n. It's actually the nearest integer to this, as it happens. So what am I really doing here? Well, I'm finding a radius of convergence of a generating function is really what I'm doing here. So if you think about, so let's use the blackboard to write down some definitions. So what are my definitions? So I just wrote down the core of m is the non-projective part of m. And I want to take Cn of m to be the dimension of the core of m tensor n. And I want to form a generating function for this. So I'm going to write f sub m of t for the sum from n equals 0 up to infinity of t to the n Cn of n. So C0 is just going to be 1, of course. I'm showing the red stuff. Cool. Okay, so if you look at this, really, if I want to know how fast Cn of m is growing, I should look at the radius of convergence of this power series. So, and if you remember back to analysis 0.1 as an undergraduate, we have a formula for the radius of convergence, which is 1 over r is, can we remember? Lim sup as n tends to infinity with the nth root of the nth coefficient. You remember that? Yes. So, for example, in this example, what is this lim sup? It's actually 1 plus root 5 over 2. So this is the invariant we're going to attach to a module. So, so definition, I'm going to make gamma, how do I write a gamma? If I need to write the group in, I'll write a sub g, but I'll sometimes miss out the sub g, equals 1 over this radius. So it's that lim sup. So there's my definition. So this is what I started to study with Peter Symonds a couple of years ago. And so in this case, gamma of m is just 1 plus root 5 over 2. So let's write down a bunch of properties of gamma of m. And eventually, what we're going to do is interpret gamma of n as a spectral radius in a commutative Banach algebra. And then we're going to use some Banach techniques to study it. But let's not do that yet. I'm not going to be able to get very far with doing that in an hour, but we can at least start to try. Okay, so let's write down some properties of gamma of m. And some of these are kind of expected, and some of them are unexpected. So the first one is, well, this lim sup is actually really just a limit. So these numbers do tend to a limit, so you don't have to worry about lim sups. So gamma of m is actually the limit as n tends to infinity of the nth root of Cn of n. And that limit is only approached from above. It never goes down below that limit. So it's actually the infimum of the set of values of the nth root of Cn of n. So it can bounce up and down above that limit, but it never goes below it. The second property is a bit obvious, is gamma of m is at most the dimension of m. Because, I mean, if you don't throw away the non-projective part, it will be growing like the dimension of m to that power. So gamma of m is less than or equal to the dimension of m, and of course it's greater than or equal to 0. So when is it 0? Well, being 0 just says that eventually some... I actually want to ask when it's n first. I'll do 0 in the property form. So when is gamma of m equal to n? This is if and only if no m tensor. Oh god. Dimension of n. That's not n, is it? If and only if no m tensor n has a projective summand. Okay, so it's usually less than the dimension. And that's if and only if there exists an element of order p acting trivially on n. So I mean, if you've got a faithful module, for example, you never get the dimension for this invariant. It's always strictly less. Gamma of m, when is gamma of m equal to 0? Well, that's if and only if some tensor power is projective, which then says that actually the module was projective. And actually then otherwise, gamma of m has to be at least 1. Well, because these CNs just take integer values. So what happens if gamma of m is bigger than 1? Well, in that case, it's at least root 2. And actually, there's an example with the square root of 2. So gamma of m is the square root of 2 if and only if, when you tensor m with m star with m, you get m plus a projective. And for example, if you take a two-dimensional representation of the foregroup, which is faithful, then it has that property. So this does actually occur. You do get root 2 happening. So, I mean, if you want to think of this as matrices, one of the group elements is going to do that, and the other is going to do that with alpha not in the ground field. When is gamma of m equal to 1 then? If gamma of m, well, gamma of m is equal to 1 if and only if m is what's called an endotrivial module. What does endotrivial mean? It means that, i.e., m tensor m star is just trivial plus projective. So an example of an m with this property is a syzygy of the trivial module. If you start a resolution of the trivial module and take a kernel, that will be an example of an endotrivial module. And actually, endotrivial modules for any finite group form an abelian group that's finitely generated. So for example, for an abelian group, you just get the syzygies of the trivial module are the only ones. An abelian P group, that is. But for non-abelian groups, you can get more complicated endotrivial groups. Okay, the list of properties goes on a bit. I apologize for that. Where are we? 7. Good. Yes. Rather obvious property is that it's invariant under taking duals. If you have a short exact sequence, M1 to M2 to M3, then each gamma of Mi is less than or equal to the maximum of the other two. The sum of the other two. That's a fairly obvious property. But even if you take a direct sum, m plus n, you only get an inequality here. It's at most gamma of m plus gamma of n, but it's at least the maximum of gamma of m and gamma of n. But you can have strict inequality here. But at least it's true that if you take a multiple of a module, so if you take gamma of a direct sum of m copies of m, then you get m times gamma of m. I mean, the problem with the previous thing here is, I mean, let's say m tensor n happens to be projective, then you would actually just get the maximum of gamma of m and gamma of n instead of the sum. It's also true that if you take a trivial plus a module, you just add 1 to the gamma. That took a bit of proving, but it's true. It's surprisingly difficult, this statement, for some reason. So the next property is that gamma of n tensor n is, again, at most, gamma of m times gamma of n. And you can have strict inequality there. But if you take a tensor power of a given module, then you get equality with gamma of n raised to the power of n. Let me actually write down a surprising property. So most of these properties are sort of, you might be able to see why they were true. Gamma of m, this property says, if you take all the elementary abelian subgroups of G and look at the restrictions of m to those, and take the gammas of those, and just take the maximum, you get gamma of n. So everything is controlled by the elementary abelian p subgroups of the group. If you've ever looked at mod p cohomology, you'll have seen this sort of phenomenon before. And this sort of suggests that it has something to do with cohomology. So I mean, there's a theorem of Schuinard, for example, which says that a module is projective if and only if its restriction to every elementary abelian subgroup is projective. And that's a sort of cohomological statement. And then Quillen proved that the Krull dimension of the cohomology ring is the maximum of the ranks of the elementary abelian subgroups, and so on. So there's some cohomology behind this. So now let me give you another example. Let's take M to be the natural two-dimensional module for SL2 p to the n. Okay. So we're just taking the 2 by 2 matrices over the field of p to the n elements with determinant 1, and there's an obvious two-dimensional module for that. Then what is gamma of n? It's 2 cosine pi over p to the n. Thank you. But actually, so now I have a conjecture, which is, you see, between 1 and 2, it's very hard to get values of gamma of n. And the only ones I've ever seen are 2 cosine pi over p to the n for some prime. So is it true that if gamma of m lies between 1 and 2, then it has to have one of those values? After 2, it's very easy to get sort of dense sets of gamma of n. But another thing we don't know is whether gamma of m is always an algebraic integer. Every example, by the way, we computed hundreds of examples of this, and we got some interesting algebraic integers out, but we never got anything that wasn't an algebraic integer. What we do know is that if you look at all finite groups, all fields, all modules, and look at the collection of gamma of m's that you get, that's a countable subset of the reals. But still, we don't know whether they're all algebraic integers. Yes, so the reason why this is true, by the way, is you start playing around with Chebyshev polynomials and tilting modules. That's all the proof I'm going to give you. So there's a bunch of properties. And what I want to do next is talk about the representation ring, or green ring, of a finite group. Oh, the blackboard's even the right colour, good. But the colour doesn't really matter. So the representation ring or green ring, after Sandy Green. And I'm actually going to use the complexified version. So A of G is the complex vector space with basis symbols of the form brackets M, where M is an isomorphism class of indecomposable finite dimensional KG modules. I guess K should really be in the notation here, but I'm going to ignore it. So that's how it is as a vector space, but we're going to put a multiplication on it as follows. If I think of positive integer combinations of these M's as just being all modules, all finite dimensional modules, Carl Schmitt says that any module has a unique up to isomorphism decomposition into indecomposable. So I can identify finite dimensional modules with certain positive elements in this vector space. And then I'm going to put a multiplication just by using tensor product. And thinking of this as a linear combination of basis elements. Okay, and then extend bilinearly. To a product on this vector space. Okay, so that's the representation ring. And then what are we doing here? Let's make a definition of a representation ideal. And I'm going to abuse some notation here. So a representation ideal X is going to be a subset of, well, actually I'm going to make it a proper subset of the indecomposables, such that if M is in X and N is any module, any finite dimensional module, then every summand of M tensor N, every indecomposable summand, is in X. So a good example of that is the projective modules. So if I take a projective module and tensor with anything, all the summands are projective. But there are other examples. So another example, so the first example was projective modules. And my second example is indecomposable modules of dimension divisible by P. And it's not quite obvious that if I tensor, this depends on the field being algebraically closed, actually. So if I take a module whose dimension is divisible by P, an indecomposable module, and tensor it with any module, every summand has dimension divisible by P. This comes from an old lemma that I proved with John Carlson back in the 1980s, about when the trivial module is a summand of a tensor product. So number one is sort of, what do I also want? I also want that M is in X implies M star is in X. I really want it to be closed under taking rules. So the projective modules turn out to be the smallest representation ideal, and the second example is the largest representation ideal. But then there are huge numbers in between, and there are some quite interesting ones. But we're going to be able to play this game that we're doing here with any representation ideal, not just with projective modules. So actually, let's write on the definition board. Core sub x of n is the non-x part of m. You throw away all the summands in x. And then Cnx of m is the dimension of the core x of m tensor n, the tensor n power of m. And then fx m of t is that. And so really I can now write gamma x of m for that lim su. So this is just playing the same game with any representation ideal. It's an obvious generalization of what we just did. And a lot of the properties go through, some of them don't. So for example, detection on elementary obedience certainly doesn't. So what does the representation ring allow us to do with this invariant? Well, we're going to complete the representation ring with respect to a certain norm, and then treat it as a commutative Banach algebra. That's what we're going to do. So let me reassure you that I'm not going to assume that anybody in this room, including me, knows what a commutative Banach algebra is. And indeed, 2 years ago, I had no clue. So let me tell you what a commutative Banach algebra is. So first of all, hang on. Oh, we've used up half an hour. Goodness gracious. So a normed algebra. This is always over C. Is well, it's associative, good, and ours are going to be commutative as well, but let me not put that in the definition yet. Algebra A over C with a unit element, which I'll call 1, and a norm, which is a map from A to the positive reals, that's written with a double bar, satisfying some properties. The norm of 1, I'm going to take to be 1. The norm of x plus y is supposed to be at most the norm of x plus the norm of y. The norm of a constant multiple of x is just the absolute value of c times the norm of x. And the norm of a product is at most the product of the norms. Okay, and if something has norm 0, that implies that x is 0. Everything else has strictly positive norm. Okay, and then, so the norm gives you a metric on this algebra, given by the norm of the difference of two elements. and then if it's complete with respect to the metric of this norm, it's a Banach algebra. So we're going to talk about commutative Banach algebras. So this subject was really started back in the early part of the last century, and Gelfand in the 1940s found out the basic properties of commutative Banach algebras, and we're going to use some of them. So what we're going to do is put a norm on A of G and then complete it. But first of all, I need to tell you what happens if I have an ideal in a Banach algebra and I quotient it out, because this is what we're going to do. We're going to take these representation ideals, take their span, quotient them out, and use a quotient norm. So ideals. If I is a closed ideal, you know what closed means because you know what the metric is, then in A, then A mod I is again a Banach algebra with the quotient norm And what is the quotient norm? Well, if I've got a coset, its norm is just, I look at the closest point to the origin. So I look at the infimum over all y of oh dear. Yes. Okay, well I'm not going to pick them all up right now. Yeah, so this is a sort of obvious notion of distance in a quotient. And it does indeed make A mod I into a Banach algebra. So what are we going to do? We're going to put a norm on A of G. Namely, the norm of the sum of some modules with some complex coefficients is just going to be the sum of the absolute values of the coefficients. These are indecomposable modules. Absolute values of the coefficients times the dimensions of the mi's. That's what we're going to do. And it's not too hard to check that that satisfies these properties for a normed algebra. So if you complete A of G, I'm going to write A hat of G in completion. And the way to think of the completion is, I mean, these were just finite sums. So elements are really infinite sums, the sum of AI, MI, with the sum of absolute value of AI, dim, MI, finite. So you're just allowing smaller and smaller copies of larger and larger modules. And then, if X is a representation ideal in A of G, then the linear span of X, if I then close it, is a closed ideal in A hat of G. And so let's think what the quotient norm is. Well, the quotient norm on, what do I want to call it? Well, it's really just A hat of G modulo that closure is the norm of the sum of AI mi is the sum of mod AI is really the sum over the mi not in X of that. So it's really, if you like, it's the sum of mod AI dimension of the core with respect to X of mi. So this is actually the thing that we were studying. The powers of an element. So how do you look at powers of an element? I'm now going to use the other blackboard. This is dangerous. Well, let's talk about spectrum. If I have an element of a commutative Banach algebra, then the definition of the spectrum of that element is the subset of the complex numbers consisting of the lambdas such that A minus lambda times the identity is not invertible. So if you think back to linear algebra, this is just an analog of the set of eigenvalues of an element. Okay, and it turns out that for any element of a Banach algebra, the spectrum is actually a closed and bounded subset of C. So it's a compact subset of C. Associated with an element. And then the spectral radius is just the maximum over lambda in spec A of the absolute value of lambda. So it's just the smallest circle you can fit all these elements of the spectrum into. And then Gelfand found a formula for this spectral radius, which you're going to recognize as something we're interested in. This is back in 1941. The radius of A is equal to the limit as n tends to infinity of the nth root of the norm of the nth power of n. So if you think of A as an element of a representation ring corresponding to an actual module, what are we doing here? We are taking the tensor nth power of the module, taking the dimension of the core, taking the nth root, and then we're taking the limit as n tends to infinity. So that is the gamma of the module. So the upshot of that is that in A hat of G modulo this closure of X, the spectral radius of a module M is gamma sub X of X. obvious from what we've said so far. And species. What are species? A species of A of G is a ring homomorphism, well, a C algebra homomorphism from A of G to C. So, for example, you're familiar with some of these. For example, you have a Brouwer species. The Brouwer species are the ones that don't vanish on projectives, and they just correspond to columns of the Brouwer character table. So just taking Brouwer character on an element is a ring homomorphism that gives you a species. So the Brouwer the species come in two sorts. They're either Brouwer species, of which there are the number of P prime conjugacy class of them, and then there are non-Brouwer species which just vanish on all projectives. So then, when is a species going to extend to the completion? Is really the next question. So when does it give you an algebra homomorphism from A hat of G to C? Well, that happens if and only if it's continuous. The species extends to A hat of G if and only if it's continuous with respect to the norm. And that happens if and only if, for all modules n, the absolute value of S of m is less than or equal to the dimension of m. The species S, extends to A hat of G, if and only if it's dimension bounded. So really the interesting species for us here are the dimension bounded species. And then we also want to know when it descends to A hat of G modulo this X. So we want to know when it gives us a map from this quotient to C. So that's if it vanishes on X, basically. So it descends to A hat of G modulo X if and only if it vanishes on X. And that's if and only if, for all modules n, the absolute value of S of m is at most not the dimension of n, but the dimension of the core with respect to X of n. So we call those X core bounded. You're going to be able to see that. Yes, good. And then, so here are some statements that one can prove. The first is that if you want to know what the spectrum with respect to this X norm of a module M is, well, what is it? It's actually the set of values of S of M such that S is an X core bounded species. So if you want to know the spectrum, you just look at the images of your module under all X core bounded homomorphisms to the complex numbers. And in particular, that says that gamma X of M is the maximum over X core bounded species S of absolute value of S of M. And there exists an S, so given M, there exists an S such that S of M is actually the real number, gamma X of M. So in other words, what that's saying is, if you look at the spectrum of this module in this sense, its spectral radius as an element is an element of that spectrum as a positive real number. So you've got this circle, and actually the right-hand end point of it is in the spectrum. So then there are, so I mean, looking at these techniques actually led to a lot of the properties that we were able to prove for this invariant gamma. But there's a fundamental question which I can't yet answer, which is the following. I can actually put a star operation on A of G to make it a Banach star algebra. Namely, I'm just going to send M to the dual of M. I'm not going to give you the axioms from a Banach star algebra, but it's, I mean, you can sort of guess what they are actually. So this makes A hat of G a Banach star algebra. And then there's a definition of a symmetric Banach star algebra, which I don't know whether or not this satisfies. But if it does, it would answer one of the questions that we don't know the answer to. So there's a question, is gamma of M tensor M star always equal to gamma of M squared? We don't know the answer to that. And what I'm trying to point out is this is true if A hat of G is what's called a symmetric Banach star algebra. And I'll give you several equivalent definitions of what a symmetric Banach star algebra is. The first is that for all S from your Banach star algebra to C, so those will correspond to our core bounded species, S of A star is equal to the complex conjugate of S of A. So the question is that true? So if I have a core bounded species, well, actually, I can just ask it for any species, any dimension bounded species. Is it true that S of A star equals S of A bar? I'd love to know the answer to that. But let me give you some statements that are equivalent to it. for all A in A star A plus 1 is invertible. You might think that you can actually answer that representation theoretically, but I haven't been able to. Then for all A in A, the spectrum of A star A is contained in the positive real line. So then the question is A hat of G a symmetric Banach star algebra with this star operation? So I do want to end with one more question, which is sort of related to everything that I've said today, which is, let's suppose that I look at the dimensions of the cores of tensor powers of a module, and just that sequence of numbers, does it eventually satisfy a linear recurrence relation with integer coefficients? We ought to be able to answer that, surely. If that's true, then these gammas are algebraic integers, for example. So there's a problem for you to get hold of. Take the tensor powers, chuck away the projectives, look at the dimensions of what's left, and ask whether that eventually satisfies a linear recurrence relation with constant coefficients. And that's a good point to end. Thank you.
Do you know the answer to that for some family of groups?
I know it for the Klein-4 group. It's the only.
Wow.
It's the only example. Well, it's true for cyclic Celof subgroup, sort of for stupid reasons. For the Klein-4 group, that's the only other example where we actually completely understand the structure of the representation ring. So there are some more examples where we know all the representations, we just don't know how their tensor products decompose.
And what's the answer?
The answer is it is a symmetric Banach star algebra in the cases where we can actually check it. But for example, for dihedral 8, we know all the modules, we don't know how they tensor. So for the quaternion group of order 8, we know that the modules are classifiable, but we don't know what they are.
But you said you did a lot of calculations of these.
Yes.
So for what kind of group could you actually do it?
So there's only ever a point in computing gamma of m for an elementary abelian P group because of that last property that I put. So actually we've been doing loads of small rank elementary abelians and modules up to about dimension 15 and just ripping away with tensor powers of them and seeing what the pattern is. And some very interesting patterns occur actually. It's really worth studying further.
Other questions?
Well, can I tell you one more conjecture? This is another really stupid conjecture. So finite 2 group in characteristic 2. If you've got an odd dimensional module, indecomposable, and another odd dimensional indecomposable, and you tensor them together, there should be only one odd dimensional summand in the answer. All the other summands should have even dimension. I mean, it's enough just to tensor a module with its dual and check that property. So if you have an odd dimensional module and tensor with its dual, you get the trivial module, but all the other summands should have even dimensions. And in fact, in that case, they should have dimensions divisible by 4. But it's a conjecture. Again, done hundreds of examples. True for dihedral groups then.
Okay, I think that's it. Thank you again.
We've got 2 to 9 now.
me in areas which will inform me about it.